and welcome back to Module 2. I am Madison Bellamy and I am going to be your presenter today. Today we'll be talking about sets and whole numbers, number theory, and chapter 3 enumerations and computations. Let's jump right into question 1. So question 1 gives us a universal set of A, B, C, D, E, F, G, and H. That universal set is divided into 3 sets of A, B, and C. In set A, we have B, C, D, G, and H. In set B, we have D, F, and H. And in set C, we have D, G, and H. Notice how all 3 of those sets at least have one letter in common, and that is going to be important for the representations that we show coming up. In part A, it's asking us to represent in the Venn diagram B union C, which is all the set B and all of set C joined in one Venn diagram. So we can see that represented in here. Because all of set B is represented in this diagram and all of set C. In question B, it's asking us to represent A intersection B, which is all the things in common of A and B together represented in one diagram, which can be shown as such, because we only have the things in common between A and B in the diagram. In question C, it's asking us to do the intersection of B and C. So just like last one, we did the in common of A and B. In this one, we will represent the Venn diagram of B and union C. Intersection C, sorry. Which is shown here because the only shaded area is the B intersection C. So only things that B and C have in common. For D, it's asking us to represent A union C, which is all the things in common between A, set A, and C. So it's set A and C and set C and the things in common, which can be represented as so. For question E is asking us to bar over A means everything that is not in set A. So you have B, C, D, G, and H in set A. So it's asking us for everything that isn't in set A, like F and A. So that would be the only things that aren't in set A that it's asking us for, which can be represented as so. So even the universal set is the one that's going to be represented and B and C. Everything is represented in this diagram except set A. For question F, it asks us to do A intersection C, which is all the things in common between A and C, which can be represented as so, because the only shaded area is the things in common between A and C. For F, we are going to have to do distributive property here, because it is asking us for the union of A and B and A intersection C. So for that, it can be represented as so, because it is the union of A and B and the intersection of A and C. All right, question 2. Question 2 says, let S, L, R, and D denote the sets of small, large, red, and blue. Of the blue shapes, respectively. The set A contains the shapes that are small and not a triangle. So A is equal to S intersection bar over T. Complete parts A through D. So it's asking us to demonstrate parts A through D. And we just learned about union and intersection in our previous question. So it's asking us what shapes are going to be L to the intersection H. So this is going to be represented as large hexagons because it is only asking us for the things in common between large and hexagon, which would be large hexagons. So the only shapes represented in A are going to be large hexagons. In question B, it's asking us to demonstrate C union hexagons, which are going to be all the sets of circles and hexagons joined together because it's the union. So those are only going to be circle hexagons. They can be small or large. They just have to be circles and hexagons. Red or blue, just circles and hexagons. In question C, it is asking us to demonstrate bar over T intersection of R, which is going to be all the things that aren't triangles and red shapes. All the things that aren't triangles but red shapes. So those would be the hexagons and the circles and all the red shapes that are not triangles. So all the shapes that are red and aren't triangles are going to be demonstrated in this. So they can be small or large, but they just have to be red and not a triangle. So that can be red circles, red hexagons, but they cannot be triangles. For question D is asking us for C, intersection of S and intersection of R. So that is going to be circle shapes that are small and red. So that is going to be all the shapes that are red, small, and circles. So that would be small red circles. Would be the only ones that could be demonstrated here. Alrighty. Question 3 says to show the Indo-Arabic equivalent of each of the following questions A through D. So we have a key here to the right. It says key right there. We need my little Z box. We have a key here to the right. So coordinating to A would be the Egyptian numeral system. These little pipe things on A represent 10,000, so we are going to have 3 of 10,000s. The little, it looks like little intersection symbols are going to be 1, 2, 3, 4, 5 intersection symbols. So they are going to be 5 times 10 because that is what is represented in the Egyptian numeral system. And in the little bars, it seems we have 1, 2, 3, 4 of those. So that would be 4 times 1 because that is what's also represented in the Egyptian numeral system. So we should have 3 times 10,000, 5 times 10, and 4 times 1, which would equal our total of 30,055. For B, we are matching this to the Roman numeral system. The N here is represented as 1,000, so we will have 1 times 1,000. C is represented as 100, so we should have 100. Yes, just 100, 1,000 minus 100 because we have the M behind C, which is equal to 100. So we should have 1,000 minus 100 plus the X's, which is equal to 10 on the Roman numeral system, 3 times 10. And then we have 5, it looks like minus 2. No, that's not minus 2. It's just 2 separately. 5 times 1, so it's really 1V, and then 2 times 1 is that represented. And it all equals 1,937. For C, we have it represented in the Babylonian numeral system, which is only systems of 1 and 10. So the arrows are 10, and we have 4 of those, so 4 times 10, and then 1, which is equal to 1. So we have 1 and 1 is equal to 41. In question D, it is significant to the Mayan numeral system, which we can see here, and this one is a little bit different. For each placeholder, it is going to be represented by a different number each time. So if we have D, one of these lines is equal to 5, so we have 5 right here, but that is going to be multiplied by 7,500. Not 7,500, 7,200. 5 times 7,200 plus this bar, if the line over it is equal to 6, so that is going to multiply by 360 because the place values are 7,200, 360, 20, and 1. So our next place value is going to be 3 dots, so that's equal to 3 times 20 because that's what our place value tells us to multiply by. And the next one, these 2 dots and 5, 10, 15 is equal to 17, and it's only 1. So we'll do 5 times 7,200 plus 6 times 360 plus 3 times 20 plus 17 times 1 is equal to 38,237. And that is all for this question. All right, we are going to be working on lattice algorithms in question 4 in the box. Multiply the problems A through D using the lattice algorithm. Well, using the lattice algorithm, we have to draw a box to represent our numbers. So in this case, we have 28 by 32 in question A. So we are going to draw a box divided by 4 because we have 4 numbers to multiply by. Alrighty. So we have 28 by 32. And what we're going to do is we're going to multiply each one using kind of like distributive property. Each one, and after all that is said and done, we will multiply diagonally to get the numbers on the bottom. So we have 2 times 3 is 6, which it's asking us for 2 place values, so we're just going to put 0 at the top. 0 and 6. 8 times 3 is equal to 24, so we'll write it out as 24. 2 times 2 is 4. Again, we're going to put that 0 in the second place value. And 8 times 2 is 16, so we're going to write that out as well. So then we're going to do addition out of the diagonals. This one stands by itself, so that's just going to be 6. 4 plus 4 is 8, plus 1 is equal to 9. 6 plus 2 is 8, and 0 plus 1 is 0. So 28 by 32 is equal to 896. We're going to do the same thing in question B. It asks to multiply 273 by 628. But this time, since we're working with 3 numbers, we are going to have a bit of a bigger box. We're going to do 9 squares this time since we have 6 numbers. Alrighty. So 2 times 6 is equal to 12. Again, with the double place values, we're going to have to write those out one on top of the other, do the diagonal. 7 times 6 is 42. 3 times 6 is 18. Then we go to the second row. 2 times 2 is 4. Again, writing the 0 in the second place value. 7 times 2 is 14, and 3 times 2 is 6. Again, writing that 0 in the second place value, and it's going to be very important. 2 times 8 in the third row is equal to 16. 7 times 8 is equal to 56, and 3 times 8 is equal to 24. So we're going to go ahead and do our addition. 4 plus nothing is 4. 6 plus 6 is 12. 2, 13, 14. We're going to put our 4, and we're going to carry our 1 up to that 8. So 9 plus 4 is 13, plus 5, 13, 15, 17, 19, 20, plus the 6 is going to equal 24. We're going to carry our 2. That's going to equal to 3, 4, 5, 6, 7, 8, 9, 10, 11. We're going to put our 1, carry that 1, 5, 6, 7, and our 1, because we're not doing any addition in our last one. So that is going to equal 171,444. All right, moving on to our third one. We still are going to have 9 boxes because we have 3 numbers that we're multiplying by this time. So we're going to put that in our graph. And again, we're going to do the same thing. 9 times 5 is 45. 6 times 5 is 30. 4 times 5 is 20. 9 times 9 equals 81. 6 times 9 is 54. 4 times 9 is 36. In our third row, 9 and 3 is 27, 6 and 3 is 18, and 4 and 3 is 12. So again, we're just going to do our addition, doing 2, adding this together to get 15, carrying our 1, that is going to equal 16, carry our 1, that is going to equal 11, carry our 1 again, and we are going to end up with 571,652. All right, and for our last one, we actually have 4 numbers in our first one. So we are going to be having 1, 2, 3, 4, 5, 6, 7 numbers to multiply by. So that means our box is going to get a little bit larger just by 1 number, but not much. So we're going to go ahead and make our boxes. Do our 4 times 2 is 8, again with the 0 in our first place value. 9 times 2 is 18, 5 times 2 is 10, 2 times 2 is 4. Then we're going to go ahead to our second row. 4 times 4 is 16, 9 times 4 is 36, 5 times 4 is 20, and 2 times 4 is 8. Now for our last and final third row, we're going to do 4 times 3 is 12, 9 times 3 is 27, 5 times 3 is 50, and 2 times 3 is 6. So then we're just going to do our addition, and after we've done so, we are going to end up with 1,203,336, and that is going to be it for our lattice algorithm. So for question 5, it is asking us to do estimation. Round to the leftmost digit to estimate the results of each of the following expressions. Then make the exact computation. So for our first estimation, we are going to round higher if it is above 5, and we are going to round down if it is below 5. So 883 It is well above 850, so we are going to round that to 900. 465, we're going to go ahead and round that up to 500. And the 134, we're going to go ahead and round that down to 100 because it is closer to 100 than it is to 250. So our estimation, and once we do all that, we get the total of 14. Now for our exact computation cost, we are going to do the problem exactly as written. And that total is going to give us 674 over 67, or the decimal 10.06. So as you can see, it's pretty close. So again, estimation, we're just trying to get the closest we can without actually doing the exact computation. So for our next estimation, we're just going to leave the 5, and we're going to do round that 254 up to 300, and we're going to round the 523 down to 500. We're just going to keep the 35 to 7 because that's pretty close as it is. And once we total that up, we are going to get 42.6. Now for our exact computation, we would get 42.7. So as you can see, it's a pretty close match there. Again, we're just looking to get the closest to the exact computation without actually doing the exact numbers. For question 3, we have 620 times 430 over 293. So for this, we're going to round 620 down to 600, 430 down to 400, and 293 up to 300. That's pretty close as it is. And once we tally it up, we get 800. 600 times 400 divided by 300 equals 800. For our exact computation, we are going to do the exact numbers as written, and we get 888.6. Again, we're just trying to get the closest we can without exactly doing the exact computation. Okay, and for our last problem, it says in problems A through D, solve by using bases other than 10. So when we normally do multiplication or division or subtraction, anything like that, we are using bases of 10. So if we're changing the bases, we are changing it to 5 or 6, as you see in these examples. And it's best to visualize this in a chart, so we're going to go ahead and draw that out. Our first question is asking, what is 432 base 5 plus 133 base 5? So we are going to make a little chart. Make this one to 10. Oops. Alright. Alright, so 5 bases, we're going to have 5 to the third, 5 to the second, sorry, I'm very much reverse, 5 to the first, and 5 to 0. So that is going to equal 5 to the 0 is going to be 1. 5 to the first is obviously going to be 5. 5 squared is 25, and 5 cubed is 125. So, based from this chart here, we are going to have our numbers. Let me extend this a little bit. So we'll write out our 432. Well, actually, we're going to represent these as dots. So we have our 432. So we're going to represent these as dots. We have 2 dots here, 3 dots here, 1, 2, 3, and 4 dots here. 1, 2, 3, 4. The next column is going to be 133. So 1, 2, 3 dots here, 1, 2, 3 dots here, and 1 dot here. So when we add 2 plus 3, we get 5. 1, 2, 5. We are going to have to trade that 5 in because we're going to look at this as dollars in a sense. So if you give someone a 5 and they were to give you change, they would give you how many ones? 5 ones, right? So this is represented as 5 ones. So this group together is going to move over here because we traded our 5 ones and 4 1 5. So we're going to add together 3 plus 3, which is 6. 1, 2, 3, 4, 5, 6. And again, we're going to have to trade our 5 in. So we're going to group our 5 since we're in base 5. 1, 2, 4, 1, little wonky, but we're going to include that 5 in there. So add a dot to the next one. We have 1, 2, 3, 4, 5. 2, 3, 4, 5. And again, we're in base 5, so we're going to group this 5 and trade it in over here. So then we are left with 1, 2, since we dragged this one over, 2, and 0. So our total is going to be 1,220. All right, let's grab our eraser so we can do the next one. Okay, so we went ahead and drew out the chart for the base 6. We have 425 plus 53. So this time we are in base 6, so we're going to switch it around. 6 to the 0 is 1, 6 to the first is 6, 6 to the second is 36, and 6 to the third is 216. So we're going to head and do our dots. We'll do 425, so we have 1, 2, 3, 4, 5. For the 2, 1, 2, and 4. 1, 2, 3, 4. So now we have 53. So we're going to do 1, 2, 3, and 1, 2, 3, 4, 5. Because we don't have a third digit, we're only doing 425 plus 53. So add these dots together, and we get 1, 2, 3, 4, 5, 6, 7, 8. So we'll have 8 dots. 1, 2, 3, 4, 5, 6, 7, and 8. Now, 8 is too many to fit in a base of 6. So we are going to group these 6 together. So, and we're going to transfer this dot over here and do 1 dot. Add the second column together. 1, 2, 3, 4, 5, 6, 7. So we'll have 1, 2, 3, 4, 5, 6, 7. So again, we have 8 in this one over here. We're going to group 6. 1, 2, 3, 4, 5, 6. There we go. 1, 2, 3, 4, 5, 6, 7. X that one out. Put that one there. All right, so now we're going to move that dot over again. 1, 1, 2, 3, 4 plus 0. And it's still 4. 1, 2, 3, 4. So now we're left to count the dots. We have 2. We have 1, 2. And then we have 1, 2, 3, 4, and 5. So our final answer will be 522. I'm going to go ahead and erase this one and get us set up for the next problem as a base 5 again. But this time we're going to be doing subtraction. Okay, so we are back in our base of 5. We have 5 cubed is 125, 5 squared is 25, 5 to the first is 5, and 5 to 0 is 1. So now we're going to go ahead and plug in our numbers, but this time we are going to be doing subtraction instead of addition. So let's plug those in, and we have 414. Do our dots. 1, 2, 3, 4. 1, 1, 2, 3, 4. Number 43. 1, 2, 3, and 1, 2, 3, 4. Alrighty. So we are having to do 4 minus 3, which is 1. So we can go ahead and put our 1 there. And now we can't do 1 minus 4, so we are going to have to borrow from our 4 over here. So we are just going to bring this dot over here. And remember, when we trade in our 5 for 5 ones, that's the same thing we're having to do with the dots. We're having to trade in 1 dot for 5 dots. So we do 1, 2, 3, 4, 5. And now we are doing 6 minus 4, which is 2. Then we are left with 3, and we don't have anything to subtract from 3, so it's just 1, 2, 3 dots. So in this problem, we are going to have 3, 2, 1, and that is going to be our answer for 414 to the base of 5 minus 43 to the base of 5. So now I'm going to erase this and get us set up for the next one, and we are still in subtraction. So for our last question, in question D, it is asking what is 403 to the base of 5 minus 24 to the base of 5. So we still have our table here set to the base of 5, so we're going to do our dots. 403, so 1, 2, 3, 0, we're going to put no dots, and then 1, 2, 3, 4. We're going to fill in our 24, 1, 2, 3, 4, and our 2. Oops, we did 3 on accident. Erase that one. All right. So we can't do 3 minus 4, but we also can't do 0 minus 2. So we are going to have to borrow all the way from our 4 on the other side. So we're going to cash in our 1 dot for 5. So it's going to move over here. So 1, 2, 3, 4, 5. Now we can borrow from this one. Move this dot over here, and we're going to cash that in for 5. 1, 2, 3, 4, 5. So now we have 1, 2, 3, 4, 5, 6, 7, 8 dots minus 4 dots, which leaves us with 4. 8 minus 4 is 4. So now we're still left with 4, so we don't need to borrow any more from our 4 on the other side. So 4 minus 2 is 2, and 3 minus 0 is 3. So our answer for 403 to the base of 5 minus 24 to the base of 5 is 324. And that is going to be it for our Module 2 questions. If you have any questions, comments, concerns, leave them below, and I will do my best to get back to you. Thank you so much for watching.